Ever wondered how Dbscan works in machine learning? Today, we peel back the layers on this popular algorithm. Dbscan, short for Density-Based Spatial Clustering of Applications with Noise, is a unique algorithm that has made waves in the world of machine learning. Unlike other clustering methods that require the user to specify the number of clusters, Dbscan does the heavy lifting for you. It operates on the concept of density reachability and density connectivity, separating regions of high density from those of low density. This makes it particularly adept at identifying clusters of various shapes and sizes, and even detecting noise or outliers in the data. So, whether you're trying to map out customer behavior, detect fraudulent transactions, or simply make sense of a large dataset, Dbscan is a tool that can help. Are you ready to dive deeper into how Dbscan works? Buckle up! Firstly, it's important to know what sets Dbscan apart from other clustering algorithms. One of the standout features of Dbscan, or density-based spatial clustering of applications with noise, is that it doesn't require you to set the number of clusters in advance. This is a significant departure from many traditional clustering algorithms where specifying the number of clusters beforehand is a must. Additionally, Dbscan has the unique ability to discover clusters of arbitrary shapes. Unlike methods that are designed to find spherical clusters, Dbscan can identify clusters of any shape, making it a versatile tool in data analysis. Lastly, Dbscan is less affected by initial configurations. While some algorithms are highly sensitive to the initial setup, leading to different results each time, Dbscan provides a more consistent outcome. Now that you have the basics down, let's move on to how Dbscan actually operates. Ready to get into the nitty-gritty of Dbscan? Here we go. Dbscan, which stands for Density-Based Spatial Clustering of Applications with Noise, is a density-based clustering algorithm. It works on the concept of defining clusters as high-density areas separated by areas of lower density. Let's break down this algorithm step by step. The Dbscan algorithm starts with an arbitrary point that has not been visited. This point then becomes the initial point for a new cluster, or turns out to be noise. From this arbitrary point, the algorithm checks whether there are a minimum number of points within a certain radius, which we call epsilon. If there are, this point becomes the first point in a new cluster. If not, the point is labeled as noise. But don't worry, this noise label is temporary and can change later in the process. Next, the algorithm looks at the nearest neighbors of this initial point. If these neighbors are within the epsilon distance and have a minimum number of points within their own epsilon radius, they are also added to the cluster. This process continues, and the cluster expands until no more points within the epsilon distance meet the criteria to be added. Once this happens, the cluster is complete, and we have our first cluster of data points. The algorithm then moves on to the next arbitrary point that has not been visited and repeats the process. If a new point is close enough to a previously defined cluster, it might be added to that cluster. If not, it could become the seed for a new cluster or be labeled as noise. This process continues until all points have been visited. At the end of the algorithm, we have a set of clusters where each cluster is maximally dense. There might also be some points that remain as noise. These are points that don't fit well into any cluster. That's the Dbscan process in a nutshell. But what happens when we apply it? Dbscan can be a game changer, but like all algorithms, it has its strengths and weaknesses. Let's dive into some key points. Dbscan is a star when it comes to finding clusters of any shape. Unlike other methods, it doesn't assume that clusters are spherical, which makes it versatile and adaptable. It's also adept at handling noise in data, a common issue that can throw other algorithms off track. However, it's not without its challenges. Dbscan can struggle with clusters of varying densities. If clusters are too sparse or too dense, the algorithm might not perform as expected. Moreover, choosing appropriate parameters for Dbscan is more of an art than a science. It requires a deep understanding of the data and a bit of trial and error, and that's Dbscan for you. A powerful tool in the right hands. Remember, the best algorithm is the one that works best with your specific dataset and needs.